In the first question, we have silver chloride, which is an ionic compound, and it is insoluble in water, does not dissolve in water. The molten silver chloride break down during electrolysis. The product are chlorine and a silver metal is there. Chlorine gas is soluble in water and it is a toxic gas. A student suggests using the apparatus shown to break down silver chloride. So in a test tube, he's having a molten silver chloride, passing a current through it, produce silver metal, which will stick to the cathode, and chloride ion attracted towards anode, produce a chlorine gas. Draw an arrow on the diagram to show where heat must be supplied to silver chloride. So where we should supply the heat energy or heat should be supplied. So heat should be supplied to the silver chloride. So we'll draw an arrow here. Then complete the diagram to show how chlorine gases can be collected and the volume of a chlorine measured. Label any apparatus you draw. So what we should draw here, because we want to collect a gas. So whenever we want to collect a gas, so it should be a gas syringe. And we can collect gas over the water, but because they mentioned it is a water soluble, so we'll draw a gas syringe here. And label this as gas syringe. Then give two observations that are made when a silver chloride breakdown. So what you will observe, as you can see, a silver chloride, a molten silver chloride, it contains a silver ion. So there's a silver ion is there and the chloride ion. Silver ion is a positive ion, so it is attracted towards the anode, cathode, the negative terminal. And chloride ion is a negative ion, so it is attracted towards anode. So what we will observe, because whenever chloride ion will move there, what will be the ionic equation? When one chloride ion is there, it will lose one electron and from chlorine atom. But chlorine is a non-metal and non-metal cannot exist as an atom, so it will always be a molecule. So when two chloride ions are there, they will lose two electron and form chlorine gas. And what is the appearance of a chlorine? Chlorine is a yellowish green gas. So what we'll observe at anode, we'll observe a yellowish green gas. And silver ion attracted towards cathode, so it will take one electron and silver will turn into atom. And it's a metal, so you will not write as the molecule, it will always be an atom. And what will be the observation whenever a metal is formed at cathode? So we'll observe a shiny solid is formed. So whenever a metal is there, so your observation will be a shiny solid. So the two observations, one is a shiny solid, another one is a yellowish green gas. Because chlorine is yellowish green, so that's why there's a yellowish green gas. In part D, the person doing the experiment followed all normal lab safety rules. State one additional safety precaution that should be taken when doing this experiment. Give a reason for your answer. Look, in the question, they already mentioned that it is a toxic chlorine, because silver ion turned into silver metal and that remain in the mixture. But what happened? The chlorine gas is released. And this chlorine gas we were collecting in a gas syringe. But maybe some of the chlorine gas might escape. And they already specified it as a toxic gas. So whenever a toxic gas is given off or a toxic gas is released, so we should always perform the experiment in a ventilated room or a fume cupboard. We can mention a fume cupboard or we can mention a ventilated room. And what is the reason for performing this in a ventilated room or a fume cupboard? So safety precaution, we should perform in a ventilated room. And what is the reason why we want to perform in a, so because as I already mentioned, chlorine is a toxic gas or a poisonous gas is there, that's why. So just one reason why zinc is not suitable material for use as an electrode. So why we cannot use zinc? Because electrodes are always made up of inert material. Inert means should not be reactive. So why zinc is not a suitable material for this reaction? Because zinc is reactive metal. So zinc is a reactive metal, it can react. That's why we don't use it. So the material which we always prefer to use as electrode, either it is made up of graphite or platinum. Then the last part, the chlorine gas was bubbled into aqueous solution of sodium salt. The color of a solution changed from colorless to orange. Identify the sodium salt and explain what happened and what has caused this color change. So remember, chlorine is more reactive. So chlorine is more reactive. When we compare the reactivity of halogens, we have fluorine, chlorine, bromine, and iodine. So as we go down the group 7, the reactivity decreases, become less reactive. So if we bubble chlorine through sodium fluoride, aqueous sodium fluoride, there will be no reaction. Why no reaction? Because chlorine is less reactive, it cannot displace fluorine. But if we bubble chlorine through aqueous sodium bromide, because chlorine is more reactive, so it will displace this bromine. As a result, what it will happen? It will produce sodium chloride and bromine. And same thing happened for iodine as well. So if it was sodium iodide, when we bubble chlorine, it will also displace that iodine and form a yellow solution or a brown solution. So they mention a chlorine is bubbled to aqueous solution of sodium salt. So there is a sodium, and what else should be there? It cannot be fluorine, it can be bromine or iodine. So example, if we are taking sodium bromide. So the color changes from colorless to orange. Why originally it was colorless? Because sodium salt like NaBr, aqueous NaBr is colorless, does not have any color. But when we bubble this chlorine, chlorine is more reactive. As a reaction occurs, the solution will turn into sodium chloride, NaCl, and a bromine is produced. And when bromine is produced in the solution will be orange in color. So the sodium salt is actually sodium bromide. And the explanation for this, why there is a color change? Because the chlorine is more reactive than bromine. So as chlorine is more reactive than bromine, it will displace bromine or bromide ion from salt. In second question, a student investigates the reaction between aqueous potassium hydroxide and two different aqueous hydrochloric acid solution A and B. Two experiments were done. A burette was filled with solution A. So we filled a burette with solution A, and then a solution A was run out of a burette so that the level of a solution A was on the burette scale. A measuring cylinder, 25 cm cube of sodium potassium hydroxide is used. The aqueous potassium hydroxide is poured into a conical flask, and then we add drops of methyl orange and its indicator. A solution A was added slowly from the burette to the conical flask, while the flask was swelled until the solution changes the color. So what we are doing in this experiment, this is the titration, like identifying the concentration of the unknown solution by a known one. So we take a conical flask, and using a measuring cylinder, we add 25 cm cube of potassium hydroxide, KOH. And then we add a methyl orange indicator here. So we add a methyl orange indicator to the conical flask, and then a burette is there. A burette is filled with solution A. So a burette is filled with solution A and we add solution A. Solution A is basically HCl. We don't know the concentration. That's why we are saying it's solution A. And we add HCl. So HCl react with potassium hydroxide until indicator shows a color change. And then what we did, we repeat the procedure. The same burette, but instead of using solution A of HCl, we'll use solution B. Like another solution. Why we are saying solution A or B? It means they have a different concentration. So we fill the burette with another solution of HCl and a different concentration. And we also take 25 cm cube of potassium hydroxide by using a measuring cylinder. We transferred that into a conical flask, that is 25 cm cube of KOH, potassium hydroxide, and we use methyl as an indicator, methyl orange. An indicator is placed here. So first it's in alkaline medium. When we add acid, acid react with an alkali until indicator shows a color change. So the first part, use the burette diagram, complete the table. So what is the initial reading? What is the starting reading on the burette? So it appeared as 18. 8, the first one. So 8.0 centimeter cube is there. And the second one, final burette reading. So it is 17.1, 2, 3, 5, 6, 7, 8, and 9. So 17.9. We'll use the bottom of the meniscus. So this is 17.9 cm cube. We don't have to write cm cube already. They specify the column, the unit here for volume is cm cube. Then what is the volume added? Like if before it was 8 and then it is 17.9. So how much volume is removed from the burette? That is the volume of acid added. So it will be 17.9 minus 8. So it will be 9.9. So 9.9 cm cube of 9.9 cm cube of this acid HCl is used to react with 25 cm cube KOH. Then we repeat the procedure. And now with solution B, we have the initial burette reading and we have the final burette reading. So what is the initial burette reading? That is 7.5 is there. So initial is 7.5 and final is 27.1, 2, and 3. So 27.3. Then we take a difference, 27.3 minus 7.5, so it is 19.8. So 19.8 for B, how much it is needed? 19.8 cm cube of B is needed, HCl. So which HCl is more concentrated, like which have more particles in a unit space? So this HCl A is more concentrated. Why it is more concentrated? Because a small quantity can completely react with potassium 25 cm cube of potassium hydroxide. Here we need a large quantity of HCl to react with potassium hydroxide, so it is less concentrated, like it contains less moles or less particles. So the one which we need, like example, the same 25 cm cube QH, but a small quantity of HCl can react and completely neutralize. Here what happened, a large quantity of HCl is needed to react with this 25 cm cube of potassium hydroxide. So it means this is less concentrated, or it contains less particles in a unit volume, or less moles in a unit volume. Then we have to state a color change. We are using methyl orange as an indicator. So first we have a potassium hydroxide is an alkali. So first it is an alkaline solution. When we add an acid, the solution changes to acid, because once all of the alkali is used up, the solution changes from alkaline to acidic solution. So what will be the color change? Methyl orange. In alkaline medium, it is yellow, but in acidic, it is orange. So what is the color change here? We will observe the starting color will be yellow and the final current will be orange. We have to learn the color change for the indicators, and depending on what is the starting medium and what is the final. So in this example, what is there in a conical flask is always the starting color of an indicator. Because we have potassium hydroxide, that's why it is alkaline, and in alkaline condition, methyl orange, we are using an indicator. It is yellow in alkaline condition. But when we add acid, it will turn to orange. Then before starting a titration in experiment 2, the conical flask was rinsed with water. Why conical flask is rinsed with water? What is the reason why we are washing the conical flask with water? Just to remove the impurity or the residue or the from experiment 1. So the main purpose is to remove the contents from first experiment. That's why we are rinsing it with water. The conical flask was not then rinsed with aqueous potassium hydroxide. State how rinsing a conical flask with aqueous potassium hydroxide would change the volume of a B needed, and explain your answer. Like what we did. So first, like we did the first experiment. So first experiment is done. We react acid with an alkali. And then what we did, we rinse with water. And we carry out the second experiment. So that was in part C1. But now the conical flask was not then rinsed with aqueous potassium hydroxide. So state how rinsing a conical flask with potassium hydroxide would change. Like if I rinse or wash with potassium hydroxide. So if I wash with potassium hydroxide, so already some potassium hydroxide, because when we rinse the apparatus, some of the content will always be there with the solvent as they stick to the wall. So some potassium hydroxide is still there. So, and then further what we add 25 cm cube of potassium hydroxide. So we rinse with potassium hydroxide and then we add 25 cm cube. So the total volume of a potassium hydroxide will be more than 25 cm cube. So now the acid which we need to react with this, we need a greater quantity of acid. Why we need a greater quantity of acid? Because first it was only 25 cm cube of potassium hydroxide. But then what we did, we rinse with the potassium hydroxide and then we add 25 cm cube. So due to the rinsing, there is some potassium hydroxide in a conical flask plus the 25 cm cube which we add. So the amount of acid which we need, that will also increase. So what would be change? Volume of a solution B needed. So we need a greater volume of a solution B. And what is the reason why we need a greater volume of solution B? Because conical flasks contain more potassium hydroxide now compared to the, like it is at more than 25. So it contains more potassium hydroxide. Then the last, this one, D1, deduce which aqueous solution of hydrochloric acid is more concentrated. So which, and when we compare their concentration, so A is more concentrated than B. And how we deduce that? Because we need a small volume for a complete reaction. So small volume of A reacted with 25 cm cube potassium hydroxide compared to B. Like from a burette, when we were using for A, we were only using that was 9.9. But when we use solution B, we need a greater volume, that was about 19.8. So We need a greater volume to react completely with 25 cm cube of potassium hydroxide. Here, the same 25 cm cube of potassium hydroxide, a small quantity can be used. So solution A is more concentrated than B, or we can say it is. Deduce how many times the concentration of a solution of hydrochloric acid. So when we deduce the concentration, as you can see for A, we have for a complete reaction, we need 9.9. And for B, for a complete reaction, it is 19.8. So when we compare, what is the ratio of the volume? The ratio of the volume is 1:2. So the concentration is also, concentration of A is twice compared to B. Like, because A is more concentrated, that's why half volume is needed. B is less concentrated, that's why double volume is needed. Then in part E, explain why experiment 1 and experiment 2 should be repeated. Why we should always repeat the experiment whenever. So we can identify here we did only like we measure the initial volume, we measure the final, and we get the volume of how much acid is used. But whenever we repeat the experiment, we can identify the errors or anomalous results, or we can find an average result which is more accurate. So why it should be repeated? To find average, which is more accurate. Or we can also say to find the anomalous result. Anomalous result means like when you have a random error is there, your result might not be in the range, that is known as anomalous. Then deduce the volume of a B if experiment 2 was carried out 50 cm cube of potassium hydroxide. Look, example, the first for solution B, which was there in a burette, and potassium hydroxide, we use 25 cm cube of potassium hydroxide, KOH. So when 25 cm cube of potassium hydroxide was there, how much acid B was used? We were using 19.9 cm cube. But now they're saying we double the volume of potassium hydroxide, the same conical flask, but greater volume, like it is double 50 cm cube of potassium hydroxide. So how much I need for a complete reaction? Solution B, if 25 is reacting with 19.9, if 25 is reacting with 19.9, so 50 will react with double of it, so 19.9 multiplied by 2. So it will be 39.6. So the volume of the B, which we need here, will be equal to 39.6 centimeter cube. Why 39.6 cm cube? Because if 25 is reacting with 19.9, so 50 will react with double. So 19.9 multiplied by 2 is 39.6. So we need 39.6 cm cube of solution B, or in experiment 2. And because reason is that because the volume is doubled, volume of KOH is double, that's why we need a double volume of HClB. Then describe one change that could be made to apparatus to improve. Look, in the beginning, we were using a measuring cylinder to transfer this potassium hydroxide into a conical flask. So instead of using a measuring cylinder, we should use a pipette. Why we should use a pipette? Because a pipette is more accurate. So we should use a pipette to transfer KOH, potassium hydroxide, because pipette is more accurate as compared to measuring cylinder. Measuring cylinder advantage is we can transfer the solution quickly, but disadvantage is it's not accurate. Describe what effect using a large conical flask. So if I use a large or a small conical flask, it does not make difference. Why? Because conical flask here we are not measuring the rate of the reaction. Rate of the reaction can be altered by changing the depth of a solution. But if you use a large or a small conical flask, but if you use same 25 cm cube in a small conical flask and we use same 25 cm cube of KOH in a large conical flask, so we need the same amount of acid for a complete reaction. So there will be no effect if we use a large or a small conical flask. So remember, in titration experiment, the size of the flask, conical flask, does not affect how much acid or alkali is needed for a complete reaction. So this was Feb March 2021 paper 6 variant 2. Next session we'll discuss the remaining two questions from this.